In this set of notes, we're going to introduce the idea of continuity, and it corresponds with section 3.2 of the textbook. So to start out, let's consider two different functions. So here we have f of x and we have g of x. And so the first thing is to notice when x is not equal to 2, both of the functions are the same. But when x is equal to 2, we see that f of x is equal to 6 and g of x is equal to 2. So to start out with, to compare these two functions, let's start by creating a plot. Alright, so the first thing I'm going to do is I am going to label my x-axis. And before I do that, I'm actually going to change my pen color. Alright, so along the x-axis, I'm going to have the x-axis start at -5, and then it's going to go up by 1 with every 2 tick marks. So I'm going to go ahead and draw those in. And then on the y-axis, I'm going to either have f of x or g of x, depending on which line I'm drawing. And here I'm going to have each of the tick marks, they're going to go up by 2. Alright, now to start out with, what I'm going to do is, since the two functions are the same when x is not equal to 2, what I'm going to do is I'm going to go ahead and plot a couple points when x is not equal to 2 to get an idea of what this function or both of these functions looks like. Alright, so starting when x is equal to 0, notice that we will have 0 squared plus 2 for both of the functions. So at 0, we see that both functions are equal to 2. Now when we have 1, we're going to have 1 squared, which is 1, plus 2, which is 3. And then notice for -1, well, if we square -1, we're still going to get 1, and so it is also going to be 3. Looking at -2, for -2, we're going to square that, that's going to be 4, and we are going to get 6. Now remember, for right now, I'm not going to consider the case where x is equal to 2 because f of x and g of x are different at that point. So next, let's go to -3. So -3 squared is going to be 9, plus 2 is 11. And then I'm going to get a similar result for 3. For 4, I'm going to have 4 squared, which is 16, plus 2, so I'm going to have 18. I'm going to have something similar for -4. And then finally, -5 squared is 25, plus 2 is 27. And again, I'll have a very similar result for +5. Alright, so what we've done here is we've just plotted a couple points which are the same for f of x and for g of x. So now I'm going to use two different colors. I'm going to start with blue, and I'm going to plot f of x in blue. So now notice when x is equal to 2, f of x is equal to 6. So at 2, I'm going to put a point at 6. And notice that for f of x, everywhere where we are not equal to 2, we are going to be approaching that same value, that 6. So this is what f of x looks like. Next, let's plot g of x. And I'm going to do that in orange. Now, g of x is going to look the same, except for at x is equal to 2, the function is going to take the value 2, so I'm going to put that dot right here. So if we want to then plot g of x would lay directly on top of the light blue line, except for when we get to this point, we recognize that only at exactly x is equal to 2, we're not going to be on this curve, so we draw an open circle. Okay. So now on this plot, we have both f of x and g of x. And what we're interested in is how f of x and g of x behave around x is equal to 2. So notice that everywhere where x is not equal to 2, f of x and g of x are the same. It is only at x equal to 2 that they differ. So what we can say here close that, is we say that f of x is continuous and g of x, and remember that was the one in the orange, is discontinuous. And again, the reason that we call it this is if we look at the blue line, if I were to put my pencil down and I were just to draw along, notice I can draw the entire blue function without lifting my pencil. So that's continuous. Whereas for g of x, if I put my pen on the paper and I tried to draw it, I would have to pick up my pen when x is equal to 2, move it down to draw the dot, and then pick it back up to finish the curve. And so that's why g of x is discontinuous. So let's look at the definition of continuous and see if we can then apply that definition to that example that we just saw. So a function f is said to be continuous at the point x is equal to c if the limit of that function as x approaches c is equal to that function evaluated at c. And so to check whether or not a function is continuous at x is equal to c, we actually need to check 3 different conditions, and we're going to look at how to do that. All right, so we're going to show that g of x but this is actually a typo. I will fix this in your copy. This should be f of x is actually the one that we want here. So in your copy, this is going to be correct. So we want to show that f of x, so that function that we just saw on the previous page, is continuous when x is equal to 2. So we're going to start by showing each of these 3 conditions. So starting with number 1. So f of x is defined at x is equal to 2 since f of 2 is equal to 6. And so that comes right from the statement of the function. All right, number 2, we need to show that the limit exists. So we want the limit as x approaches 2 of f of x. And I claim that that does exist. And we could use methods that we've seen previously, but to make that argument, we can just look here at the plot to see this. We can see as we come from the left that the blue line is approaching 6. And as we come from the right, the blue line is also approaching 6. So we know that that limit exists, and in fact, we know that that limit as x approaches 2 of f of x is equal to 6. So then number 3 essentially combines 1 and 2, and we know that the limit as x approaches 2 of f of x is equal to 6, and f of 2 is equal to 6, and so therefore f of x is continuous at x is equal to 2. Now, in contrast, if we look at g of x that we had on the previous page, so for g of x, let me change my pen color here. Let me change it over to orange. So g of x on the previous page will satisfy number 1 and number 2. But for number 1, notice that g evaluated at 2 was equal to 2. So the function exists at 2. But if we look at number 2, the limit as x approaches 2 of g of x, it exists and it is equal to 6. And we can see that again looking at the graph. As we come from the left, the orange line is approaching 6. And as we come from the right, the orange line is also approaching 6. So the limit of g exists, but the limit in 2 is not equal to the value in 1, so condition 3 is not satisfied, and g of x is discontinuous. All right, so let's look at several examples here. So for the first one, we're going to show that the function is continuous at the given value. So first, we are going to note that f of x is defined at x equal to 0. And so notice the reason that we're concerned with whether or not f of x is defined at 0 is because the value that we're given here is at 0. So we're looking for continuity at 0. So it's possible for functions to be continuous at one point, but discontinuous at other points. So next, we could use our limit laws. So notice if I'm interested in the limit as x approaches 0 of negative x, because negative x is my function here, using the limit laws that we've seen previously, this is equal to negative the limit as x approaches 0 of x. So that's going to be equal to negative 0, which is equal to 0. And then finally, since f of 0, so that's our f of x evaluated at where x is equal to 0. Notice if I plug 0 into this function right here, that's going to be equal to negative 0, which is equal to 0. And that's equal to the limit as x approaches 0 of f of x. So in other words, the limit as x approaches x is equal to the function evaluated at 0. So therefore, f of x is continuous at 0. And then just double check to make sure I said that correctly. What I was meaning to say was the limit as x approaches 0 of f of x is equal to 0. And the function evaluated at 0 is equal to 0. So therefore, f of x is continuous. All right, let's look at another example. What value must you assign so that f of x is continuous at x is equal to 3? And here is our f of x. So notice what this is saying is we need to find the value a so that the limit as x approaches 3 of f of x is equal to f evaluated at 3. This is what we need in order to have continuity here. Right? So, plugging in what some of these things are, we need the following. We need the limit as x approaches 3 of 3 plus 2x minus x squared divided by x minus 3 to be equal to the function evaluated at 3. And notice right here that the function evaluated at 3 is going to be equal to a, so we can set that equal to a. So the very first thing we're going to do is we're going to evaluate the limit. Now remember, when we evaluate the limit, we're really concerned with as x approaches 3, not x equal to 3. So in other words, oops, bring that back where it should be. There we go. If x were equal to 3, we'd have that problem in the denominator. But we're not going to have that because, again, we're going to approach 3 but not be equal to 3. So first, we're going to note that 3 plus 2x minus x squared, well, that's equal to x minus 3 times minus x minus 1. So we have factored that. And often when you see a quadratic term, especially if you've got something in the denominator below it, often try to see if you can factor that to where you've got that term that's in the denominator as one of the terms here. Oops. Well, let me rewrite that now. Okay. So notice what this is going to give me. And notice I'm not making that an equal sign. That's an arrow saying, this is going to lead me to. If I'm interested in this full piece here, I'm going to have 3 plus 2x minus x squared divided by x minus 3. Well, that's going to be equal to x minus 3 times minus x minus 1 divided by x minus 3. And then we're going to have these two pieces cancel out. So this is just equal to minus x minus 1. And then again, the reason that we can do this and cancel that x minus 3, and this is an important piece here, is because we're interested in the limit as x approaches 3, not x equal to 3. So we say when x is not equal to 3. Because if x were equal to 3, we'd have 0 in the denominator, so we couldn't make that cancellation. And so this is only true when x is not equal to 3. But again, that's fine because we're evaluating the limit here. So again, we are interested in x as it approaches 3, not x equal to 3. So therefore, the limit as x approaches 3 of 3 plus 2x plus x squared divided by x minus 3, well, that's going to be equal to the limit as x approaches 3 of minus x minus 1. But notice this is equal to minus the limit as x approaches 3 of x plus 1. And then again, using our limit laws, this is equal to minus the limit as x approaches 3 of x plus the limit as x approaches 3 of 1. And then, of course, that's going to be equal to minus 3 plus 1, or minus 4. So, therefore, since the limit as x approaches 3 is equal to minus 4, what that means in order for this to be continuous is we need f of 3 to be equal to minus 4, or we need a to be equal to minus 4. All right, and one more example here. Determinant at which points f of x is discontinuous. So the first thing to notice here is that f of x is a rational function. So just as a reminder, and I'll write this down the bottom in red, So recall that a rational function is a function of one variable that can be represented as f of x equal to p of x divided by q of x, where p and q are both polynomials and q of x is not equal to 0. So notice in this case, this is a rational function because in the numerator we have 1, so we could set our p of x to be equal to 1 and our q of x to be equal to x squared minus 1. And the only variable in this function is x, so this is a rational function. And now, since this is a rational function, it is going to be continuous anywhere it is defined. And you'll actually see a rule on the next page that's going to help us with that. But, let me finish writing that out. So, it is continuous wherever it is defined. And so I'm going to put a little note here. This is going to come from the next page. So just believe me on that for just a moment. So therefore, we just need to figure out where this function is not defined. And since there is a fraction here, we know it's not going to be defined any time that we would end up with a 0 in the denominator. So we just need to determine which values would make the denominator equal to 0 in this case. So to find that, we could just set x squared minus 1 equal to 0. And notice this becomes x squared is equal to 1, or this is equal to x is equal to plus or minus 1. So it can be a negative 1 or a positive 1. So here we would say discontinuous when x is equal to 1 or x is equal to negative 1. We could also be continuous from the right or continuous at the left, very similar to how we can look at limits from the right or left. And then using the limit laws, we could find that the following statements hold for combinations of continuous functions. And then further, we can say that f is continuous on an interval if f is continuous for all x in that interval. And then finally here in the box we have several different types of functions that are continuous whenever they are defined, and you'll notice that one of them is the rational functions from the previous page. All right, so let's look at some more examples, and I will say your book does give several examples of these, so I would take a look at those examples in the book. So we're going to try to show that f of x, which is equal to the square root of x squared minus 4 for the absolute value of x greater than or equal to 2, is continuous from the right at x is equal to 2 and continuous from the left at x is equal to negative 2. So the first thing that we're going to do is plot this function. So to plot this function, I'm going to start out with on the x-axis. I'm going to start with negative 5, and for every 2 ticks, I'm going to go up by 1. And then along the y-axis, I'm going to start at 0, and then for every 2 ticks, I'm going to go up by 1. And now I'm going to try plotting f of x. So first of all, notice that f of x is only defined for when the absolute value of x is greater than or equal to 2. So looking at my x-axis, what that means is I'm really only interested in plotting in this region and in this region here to the left. And because, for example, if we had -2, the absolute value of -2 is 2, which is obviously greater than or equal to 2. Right? Next, we're going to go through and just plot a couple potential values, and then we'll actually draw the functions. So let's start at 2. So when x is equal to 2, we're going to have 2 squared, which is 4, minus 4 is 0, and then of course the square root of 0 is 0. So we will have a 0 here. Very similar for -2. -2 squared is 4, minus 4 is 0, and the square root of 0 is 0. Next, when x is equal to 3, we're going to have 9, minus 4 is 5, and then the square root of 5 is approximately 2.24. So we're going to go up to 2, let's see, 2, and then about a quarter of the way up. This isn't going to be exact. And then notice for -3, we would get the exact same thing. All right, for 4, we're going to have 4 squared is 16, minus 4 is 12, and then the square root of 12 is 3.64. So here at 4, we're going to go up to 3.5. That's about 3.64. And then similar for -4. And again, this isn't exact, but it gives us an idea of what this looks like. And then if we connect the dots, this is what our function looks like. Again, not an exact, but it gives us an idea. So now we can go through and actually show that our function f of x is continuous from the right at 2 and from the left at -2. So first, what we're going to do is we're going to let g of x be equal to the square root of x, and we're going to let h of x be equal to x squared minus 4. And so you might ask, well, why would we want to do that? Well, if we look at our function that we have up here, f of x, notice that we've got the inside of the function, which is x squared minus 4, and then around that we've got the square root. So really what we've got here is what we call a composite. So we've got one function, which is x squared minus 4, inside of the square root function. So in other words, notice that f of x is really equal to g of h of x, and this is also written as follows. It's written as g circle h of x. And so all of these, when we define g of x and h of x this way, mean the same thing. All right, so we know that h of x is continuous. And we know that because it's a polynomial. And remember that polynomials are continuous anywhere that they are defined. So we know that it's continuous, and h of x is greater than or equal to 0. So therefore, g of x is continuous at h of x. And we know that because g of x is equal to the square root of x, and the square root of x is continuous anywhere that x is greater than or equal to 0. And the limit as x approaches 2 from the right of g of h at x is equal to the limit as x approaches 2 from the right of g of h of x, which is equal to the limit as x approaches 2 from the right of g of h evaluated at 2, h of x, which is equal to g of h at 2, which is equal to g of 0, which is equal to 0. And then similar for the left, we could show that the limit as x approaches 2 from the left, -2 from the left, of g of h x is equal to 0. And so since f of 2 is equal to the square root of 2 squared minus 4, which is equal to 0, and we can show that f of -2 is equal to 0, we have that f of 2 is equal to the limit from the right and f of -2 is equal to the limit from the left. Therefore, f of x is right continuous at 2 and left continuous at -2. And if we go and we look at the plot, this makes sense because if we're coming from the right and we are approaching 2, notice that this function moving from the right, we see that it is approaching 0, and the function evaluated at 2 is equal to 0. But if we're moving from the left, notice that the function is approaching -2. Right. As x is approaching -2, the function is approaching 0, and the function evaluated at -2 is equal to 0. So this is an example of a function that is right and left continuous at x is equal to 2 and -2, but is not continuous at x is equal to 2 or x is equal to -2. So in other words, to say that again, f of x is right continuous at x equals 2, but not continuous. And f of x is left continuous at x is equal to -2, but not continuous. And I should say at x is equal to -2, and up here that should be at x is equal to 2. All right, so that's an example of right and left continuous. So as always, make sure that you read through the examples in the textbook. There's lots of more good examples there, and if you have any questions, please let me know.